Okay, this is chapter 4.4 in the book. We're going to go back to factoring, but now what we're going to be factoring is we're going to be factoring problems that have x cubes, x to the 4, stuff like that. So they're going to require a little more factoring than we've done before. When we factor something like that, one of our factors could be, like we may end up with something that'll be an x squared term in itself, and we may have to factor then the x squared term. So we're going to have to use the techniques that we learned last chapter about factoring quadratics in addition to some new factoring techniques. One thing is the factoring will never go away. We'll have that in this entire course. So a couple things is the two factoring things we're going to learn today is factoring out a common factor first. And don't forget that unless it's an equation with an equal to sign, we need to keep that factor there. We just can't get rid of it. We have to continue on through the problem. So it has to remain in the final answer. After we remove the least common, or remove the common factors, we're still going to have to factor the other part of the expression, maybe. And what that could be is we may end up with a quadratic, like I said. So remember the type of factoring that we had for quadratic equations. We had the basic factoring technique. We had an AC middle and we had a difference of squares. And I'm going to show you those, right now, real quickly, just do a real quick review. Okay, so here's a couple factoring techniques that we used when we had quadratics. Do you remember something like this? It was an x squared, and there was a 1 in front of the squared term. And what we would do is we'd say, well, this is a basic factoring if we had two numbers that add to 3 but multiplied to negative 54. It was just the easy factoring. Then sometimes we had factoring that had all three terms, an x squared, an x, and a constant term. But the coefficient in front of the squared term was not a 1. Like over here, it's a 1, but over here it's not, and we would have to use AC middle. Then the third type of factoring we did with quadratics is sometimes we didn't have the x term, and it could have been a difference of squares. If the first term was a perfect square and the second term was a perfect square and they were subtracted, then that would be 7x minus 10 and 7x plus 10. So those were the three main factoring techniques that we used for quadratics. So here are some examples of equations that have polynomials where the degree is greater than a quadratic, and for these we're going to remove the common factor first. Like we're only going to do two types of new factoring today, and this is going to be removing the common factor. In the book it may call it removing the LCD. Anyway, so we're going to look at this one, and we're going to say what can I pull out of there before I even start factoring it. And I've got an x in all the terms, so I can definitely pull an x out, and I can't pull any numbers out. So when I factor the common factor out, I'm going to have x squared minus 4x minus 5. Now then, I still have a quadratic left. Maybe I could factor it, and sure enough, this is the basic factoring where I have two numbers that add to negative 4. I need to add to that. I need to multiply to negative 5, and those numbers would be, the x still has to be pulled down. It has to stay with me because there's no equal to sign. This would be x minus 5 and x plus 1. So there I'm done. That's my factoring. Okay, let's look at the next one. I have to pull out a common factor. It looks like I can pull out a 3. And it looks like since I have a y cubed in both of them, I can pull a y cubed out. That would give me with y squared, if I pull a 3 out of the 48, I get 16. Okay, so let's look at the quadratic piece, and that's a difference of squares. Perfect square for the y squared, perfect squared for the minus 16. So let's factor that. That'd be y minus 4, y plus 4. Don't forget the factor that you pulled out at the start has to go all the way down because you can't divide it out. Let's look at the last one. A 5 can come out of all those terms. And since there's a z squared in the last term and a cubic and a fourth power, a z squared can come out. That would give me with z squared plus 6z plus 9. So let's look at the quadratic. Two numbers that add to 6, multiply to 9. That would be 5z squared, z plus 3, z plus 3. And probably a simpler way to write that, since I have two factors, the z plus 3, that are the same, I'm going to write it z plus 3 squared. Either one of those would work. Okay, the second factoring technique that we're going to learn today is something called the sum or difference of cubes. And once again, we need to get the common factors out of there first, and we have to carry any of those factors down all the way to the end. And of course, unless I have an equal to sign, then perhaps I can divide them out, but you can never divide out a variable. Never divide the variable out. So once I get through factoring out any common factors, how I can tell this form is I'm going to have two perfect cubes left. They'll either be added to each other or subtracted from each other. And what we'll do is we'll find the a and b. There's a formula we're going to use for that. And then we just plug the things into the formula. And these are the two formulas right here. Okay, so the first one is called the sum of cubes. It would be if I see a perfect cube plus a perfect cube. When I see that, it will break down into this formula right here. And you have to memorize that. I won't give you that. So you'll memorize that. One thing to note is you see this squared term right here. This is a squared term. Now, I know it's just a formula right now, but we're going to see it with numbers. You can never factor that. That's going to give you imaginary numbers. So when you have a sum or difference of cubes, the squared term that you get out of it, you're just done. You don't have to try to factor that anymore because you'll get imaginary numbers. And here is the formula for the difference of cubes right below it. So we'll be using that. So let's take a look at a couple examples of how we use these things. I guess one thing to point out real quick is for the negative formula, I'm going to need to find the subtraction. I need to find the a and the b, and we'll see that. But the b will never be negative because the formula itself has a negative or subtraction sign in it. So the b will be a positive number when I pull it out. There won't be a negative number in there. So let's go do a couple examples. This is how you use this. So the first example, I'm working along and I see that I have a cubic. Now notice that I don't have any squared terms, or I don't have any x terms. I just have a cubic and a number. That's the first indication it could be a difference of cubes. So we look at the first term and it is a perfect cube. It's x cubed. I look at the second term and it's a perfect cube too. It's 5 cubed. 5 times 5 is 25. Times 5 is 125. So when I have everything factored out that I can get out of it, I simply look at the first term and I say, okay, what's the cube root of that? What's the cube root of x cubed? Okay, a would be equal to x. I don't want the x cubed. I want the cube root. For the 125, and remember, the formula already has the negative built into it, or the subtraction, so I don't care about the subtraction sign. I'm just looking at the 125, and I'm saying, okay, the cube root of 125 would be 5. So what I did is I found a and b that I can plug into my formula, and that's all I'm going to do. Okay, let me go back through this, and just so you can see how this is written, if this would be compared to the formula that I have up at the top, if this would be a cubed minus b cubed, then you could see that a is actually going to be the cube root of the x cubed, so that would be a is equal to x. The b then would be equal to 5. So I'm going to put those into my formula, and I'll rewrite the formula here. So for a subtraction, it's going to be a minus b times a squared plus a times b plus b squared. So I found my a and b. So I'm just going to plug those in. So the first part says a minus b, okay? X minus 5. Then it says a squared. So here's x. I'm going to square it. Then it's going to say plus a times b. So a times b would be 5 times x. And then last part of the formula says plus b squared. So there's b at 5. So I'm going to add 25. And there's my answer. And remember that for the squared part, you say, can I factor that? No, you can't factor it. This will be an imaginary number. It always will be. So I'm done. Okay, let's go to the next one. And what I see here is I probably can factor something out at the start. So when I see that I have an x squared and an x fifth, I know I'm going to be able to factor an x squared out, and I'm going to pull a 2 out of there also. So if I pull a 2x squared out of this, I get 8x cubed plus 27. All right, so can I factor that? Let's take a close look at it. There's no x squared, there's no x, so maybe it's a sum of cubes. Let's take a look at the first term, 8x cubed. Yeah, that's a perfect cube. Let's take a look at 27. Yeah, that's 3 times 3 times 3. So according to the formula that I have, well, let's go ahead. Then a, this would be this little piece here, where I'd have 2x squared, right? I'll bring that down in a minute. This little piece here is the same thing as saying a cubed plus b cubed. So a would be equal to 2x, b would be equal to 3. Okay, so let's use the formula that I have. And the formula is a plus b times a squared minus ab plus b squared. That's the formula for a sum of cubes. Now I memorize it. You'll have to memorize it too. So let's go ahead and plug the numbers in. Now remember, I have this 2x squared out there, so I have to include it. Now then, the formula says a plus b, 2x plus 3. Okay, now the formula says to take a and square it. A is 2x, right? So 2x squared, if I was doing that, that would be 4x squared, right? So I'm going to have to square the 2 also. So 4x squared minus a times b, okay? A times b would be 6b, or 6, what do we got here? 6x. And then lastly, it would be plus b squared. B is 3, so I would put a 9 there, and there's my factor. Once again, I can't factor the squared term. Let's go to the last one. And we see we can factor something out at the start, so I'm going to factor out a 2, negative 2, so those become positive. I can factor out also an x squared. If I do that, I'm going to get 8x cubed plus 125. All right, no x squared term, no x term, so maybe it's a sum of cubes. Yeah, 8x cubed. That's a perfect cube. 25 is 5 cubed. So a would be equal to 2x, the cube root of the first term. B is equal to 5, the cube root of the second term. So once again, I'm going to write the formula down just so that'd be a plus b, a squared minus ab plus b squared. That's the formula for a sum of cubes. So the minus 2x squared comes on down. Then I put a squared, 2x squared. That would be 4x squared. Oh, forgot a piece. Okay. A plus b, that would be 2x plus 5. Now I do the a squared. That's 4x squared plus a times b minus a times b. So a times b, I've got 2x times 5. That would be minus 10x. And then plus b squared. B is 5, so I just put 25. And there's my answer.